All right, guys, here we go. Here we go. Y'all ready? All right. So hopefully this looks familiar to you. If it doesn't, I apologize. Blame it on the pandemic. The equation of a circle centered anywhere looks like this. If Rx equals Ry, you have a circle. Does that look familiar to you guys? Nothing, not even. If Rx does not equal Ry, you have an ellipse. Yeah, go ahead. Don't worry, this is going to be uploaded to my channel earlier tomorrow. That's a knot, yeah. This is common notation. Maybe you've seen it. Yeah, that's a 1. Maybe you've seen it like an H or a K. Maybe you've seen it like... Maybe you've seen it like this. I don't know. Where the center is HK. Never? Maybe you've seen it this way then. There's so many different ways, guys. There's so many different ways. Maybe you've seen it that way. If the radius is 1, maybe you've seen it this way. I'm going to change the color. If R equals 1, yeah, you don't have to write them all down. You just need to write like this one. And all the others are derived from that. If R equals 1, maybe you saw it like this. Y equals plus minus square root 1 minus x squared. The one in blue is a circle with radius 1 centered at origin. Circle of R equals 1, comma, centered at origin. Chop, y plus minus. The plus will graph the top half, the minus will graph the bottom half. Don't worry about copying those down. They're not necessarily all that important. They're just circles. Here's the calculator. Don't worry. I'm going to put it back. If I go to y equals, and I have some junk in there, let me clear it. And I type in square root of 1 minus x squared. And I go to the bottom one, and I go square root of, I got to put a negative in the front. Second, insert negative. And I go the same thing. 1 minus x squared. Notice the different colors, the blue and the red. And I push graph. Okay, let me zoom in on that. Zoom in. It looks like an ellipse, but it's a circle. The reason why it looks kind of like whatever is because it's not a square window. If I click on window, if I click on zoom and click on number 5, there you go. Now it looks like a circle. Cool, right? Or you guys don't think that's cool? Yeah, I think that's really cool. What do you think? Let's take a guess. What do you think happens if I change that 1 to a 81? Yeah, it's gonna be bigger. The radius is now 9. Second insert. Check it out. Graph. Well, we gotta zoom out now. Zoom out. Look. Yeah, I think it's cool, guys. Don't freak out. It's just this equation. Now, you should have seen it the very first time in its most basic form. You should have seen it in geometry in its most basic form. And then in geometry, you should have talked about circles and you should have talked about ellipses. But when you guys took geometry, we were in a full-blown pandemic, and there's only so much you can learn through a little monitor. So yeah. It's like a circle. If you push down on a circle, it turns to an ellipse. Like an oval. Like an egg. Yeah. Circle of radius 1. Center at origin. All right, we have some special angles on the unit circle. Oh, by the way, why do they call it a unit circle? Because r equals 1, so it's 1 unit, the radius. And the special angles are these. So draw an axis, an x and y axis, and you don't have to be perfect. And then just draw a circle. And I know that I have a digitizer, so I can probably put like insert shapes and all that, but whatever, it's okay. I don't like my scale there. All right, so here are my special angles. Start by 30 degrees away from the x-axis, go counterclockwise. So this is 30-degree angle. Then you're going to go in increments of 15 for a little bit, just two hits. Look, there's one, so that's going to be a 45-degree angle. And here's another. That's going to be a 60-degree angle. And now you're back at a 30-degree hit. From that to that is 90 degrees. And you continue the pattern. From 90, add another 30, so 120. Then you're going to go another 15, so 135. Then you're going to go another 15, so 150. And then that's 180 right here. And you continue the pattern again. What? I just heard something divided by 4. Yeah, I guess you can do 360 divided by 4, 90. And then 180 plus 30 is 210. And then add another 15, so 225. And add another 15, so that's 240. And then another 30-degree gap, so that's 270 here. See? And then add another 30-degree gap, that's 300. And it's not to scale, don't worry. And then 315. Then 330. And then if you go another 30 degrees, that should be your full revolution 360. Do you see how we did it, guys? In a little bit, don't worry, we're going to have a big circle, and you're going to fill them all in. Nice and neat. If you see the big circle and you want to go ahead and start with the degrees, I guess that's fine as well. How do we feel? Do we feel okay? Okay. All right. Let's go to the next page. Well, I got some, you know what? Let's talk about radians before we go to the next page. I got some white space here. 30 degrees in radians. 30 degrees, and I want to turn that to a radian. So I know I take my 30, and do you guys remember from last week? I multiply this by, oh man, not everyone at the same time. Pi over 180, yeah. 3 goes into 18 6 times. So this must be pi over 6 radians. So at 30 degrees, that's pi over 6. What about at 45 degrees? What is that in radians? Pi over 4. Chav, how'd you do that so quick? I didn't. I just did 45 times pi over 180. I know that 90 goes into 180 twice. 45 goes into 90 twice. So 45 must be going into 184 times. 60 degrees into radians. Well, again, if I'm going to multiply 60 by pi over 180, 6 goes into 18 3 times, so that must be pi over 3. So pi over 4, pi over 3. Yay or nay? And then the 90 degrees, that's pi over 2. Hopefully that one's automatic, but if it's not, no big deal. The more you practice, the better you get. Hopefully by now you're getting a little comfortable with degrees and radians. Well, with degrees you've always been comfortable, but hopefully now radians are pretty cool. All right. Here we go. Ready? I have two special right triangles that make up a unit circle, the 30, 60, 90 and the 45, 45, 90. Hopefully you remember n square root of 3 and 2n for the 30, 60, 90, the properties of the sides, the relationships. And then the 45, 45, 90 triangle is n square root of 2. You guys remember that? Cool. 2n. So I have the first quadrant of the unit circle here. I'm going to fill in what I know. I know that I start at 0 degrees, so I put a 0 there. So then what did I tell you in the last page? That the first one is a 30-degree angle. So I put a 30, then I put a 45, then I put a 60, and then I put a 90 up there. So you're going to have to know those. And then if I do one revolution, that's 360 degrees. So I went ahead and put the 360. You don't have to, but since it's there. And then since we already did the radians, I already know that 30 degrees in radians is pi over 6. 45 is pi over 4. And 60 is pi over 3. And then 90 degrees is pi over 2. And I use that little dashed line to do my fractions. And in radians, of course, this is still 0 radians, so you can put a 0 there. And if I do one revolution, that is how many radians? One revolution is, 2 what? 2 pi. If someone ever asks you, where do 2 pi radians come from? Well, circumference of a circle is 2 pi radians, so I guess it probably came from there. It did, by the way, come from there. I'm not saying I guess, it did, but you can make your logic from there. This is a measurement of rotation, so it doesn't matter how big something is, or small, how big a circle is, or big. If it does one revolution, it does 2 pi radians. Cool? Okay. Now, how much it travels depends on the size, but that's a different story. We're not going to get there yet. All right, here we go. Ready for this, guys? This is the unit circle, so the radius is 1. So write r equals 1. I want to find out those coordinates. So if r equals 1, the easiest coordinates are at 0 and at 90 degrees. This coordinate must be 1, 0. And this coordinate at 90 degrees must be 0, 1. Yay or nay? Yay. I'm looking at this triangle here in blue. And I'm going to cut it and paste it in a little bit so you guys can see. So do you guys see that triangle there in blue? That is a 30, 60, 90 triangle, right? Let me see if I can grab the whole thing. Can I grab the whole thing? Man. Nope, it's not going to let me. I wanted to use technology to copy it and paste it, but let me see. Maybe it'll let me if I just do it in one swing. Wait, let me try it. Yay, it did it. Duplicate. Okay, there's my triangle. It's kind of cool. I'm going to put it over here. Okay, I think it's cool. So there's that triangle. It's the same one, right? This is my 30 degrees right there, and I know that my right angle, my hypotenuse is not perfect, but there it is. That's my hypotenuse. That's a 1. I want to figure out the length, the horizontal displacement and the vertical displacement. I know that that's 30, so this must be 60 degrees. So here we go. In my 30, 60, 90 triangle, since my hypotenuse is 1, I can say 2n equals 1. I'm going to write it here on the side. 2n equals 1. So divide by 2, n has to equal a half. My short leg is my vertical displacement here, so that's a half. Do you guys see that? Okay. Then to get my long leg, the 60 degree, whatever is opposite 60 degrees, I'm going to have to multiply that by square root of 3. You can, if you want, write 1/2 with a square root of 3 on the side, and that's perfectly okay. UH actually has answer choices like that. I don't like that answer choice, but that's fine. I prefer square root of 3 over 2. They're both correct. But square root of 3 over 2, in my opinion, is more correct. Not that my opinion matters, but, cool or not cool. So that's my horizontal displacement. So coming back over here, here's what you're going to write. I'm going to write square root of 3 over 2 as my x coordinate. 1/2 as my y coordinate. Is everyone okay with how I got those numbers? Yes, yes, yes. So because I have a 30 degree there, all I did was, here's my triangle. This is a 30, 60, 90 triangle. The hypotenuse was 1. So to get the short leg, I had to say 2n equals 1. So divide by 2, and I got n equals 1/2. This is n. And then this guy right here is n squared root of 3. So since this is n, how do I know that's n? Because it's opposite by 30 degrees. So if this is 1/2, then my long leg has to be 1/2 times square root of 3. This distance here is a vertical displacement. So it must be the y value because this is 1/2. And then this distance here is a horizontal displacement from the origin to way over here. So that must be an x value because it's talking about this value there. Does that make sense? It's okay to say no if it didn't make sense.
I understand how you got it, but like, how do you determine like where you place them? Like, why isn't it like?
Oh, yeah, good question. You see this triangle? This, do you agree that this coordinate right there is x comma y? Well, that x is the distance from here to there. So that if that's square root of 3 over 2, then that x here must be square root of 3 over 2. Because it's the horizontal displacement. Does that make sense? And then my vertical displacement, this y value is the distance from the x-axis to the top of that green point up there, which is that 1/2. So here's the x-axis to the top of that point, which is that y value. Cool? I want to be the Michael Jordan of math teachers, miss. Just ask. It's all good. All right, what's the next question, guys? Hit me with more, because I know there's more questions. So everyone's good. All right, make sure, guys. All right, there is another 30, 60, 90 triangle in here. I don't know if you can see it. Well, hopefully you can see it. There's a 60 degree there, so that must mean that this one here, let me use a different color. Let me use green. This one here in green is another 30, 60, 90 triangle. Do you guys see that? It's another 30, 60, 90 triangle. The only difference is the 30 degrees is up here and the 60 degrees is this guy. So because of that, what do you do with those coordinates? You can just what? Yeah, switch them. There's a nice word. I like to use the word toggle. The word toggle, no, it's a funny word. If you ever take have you guys ever done like a summer camp with logic, AND gates, OR gates, AND OR gates, XOR gates? Okay, there's something in logic called toggle. If it's on, then you toggle it, it's off, toggle it, it's off. Sometimes it could also mean like switch, like, oh, switch your X and Y, toggle. So there's also like flip-flops, like JK flip-flops, T flip, like, okay, if you're in engineering or you practice logic gates, you'll see what I'm talking about. Have you ever seen this shape, an AND? There's like two little sticks sticking out of it. No? An XOR? You guys don't know what I'm talking about? Never seen it? Okay, then don't worry about it. It's just logic, digital logic. It's a fun class if you ever take it. I don't know if VHDL is still a big deal. Digital logic with VHDL. By now there's probably a whole bunch of different programming. But it's really fun, guys. You should check it out. Just Google it whenever you get a chance. Okay, 45 degrees. You guys ready? I have a triangle right smack in the middle. This one here in red. That's a 45, 45, 90 degree triangle. Oh yeah, look, I was able to, yeah, duplicated it. I'm getting really, see, that's what I get. God just punished me. I was getting really good, but then he's like, nah, you're not that good. All right. You know what? Delete. Pretend that I was able to successfully duplicate that, and I'm going to put it right smack here in this white space. So here is this triangle, that red one, not to scale. Pretend it's the same one. I know it's really small, but look, if I zoom in, it's really big now. 45 degrees, this is one. I need to know I need to know those legs. Hopefully, real quick, hopefully at the very, I don't want to say, well, yeah, it is. Those legs are going to be the same length. We know that, right? It's a right isosceles triangle, 45 degrees there. This is 45 degrees up here. So because they're both 45 degrees, they'll both create equal segment lengths. Cool? All right, perfect. So in a 45, 45, 90 triangle, you have this relationship. N square root of 2. That 1 is for the n square root of 2. So I'm going to write n square root of 2 equals 1. And I'm going to get n by itself by dividing by square root of 2. And here's my answer, 1 over square root of 2. You can leave it like that, but for whatever reason, Delta and everyone else, they want it without a square root of 2 in the bottom. And I remember chatting with a professor about why that is. I don't know if this is accurate because, I didn't read it from a book. It's just one man telling me. He told me that a long time ago they used to do like log rules and tables. And to be able to use these log rulers and tables, you had to have a square root in the top, not the bottom. And I'm like, okay, whatever. That doesn't really make sense to me, but whatever. So nowadays they want you to rationalize it, guys, and to do that you gotta, well, even back then, right, that's where they got it from, multiply the top and bottom by the square root of 2 over the square root of 2. So square root of 2 over 2. I haven't officially found a legit reason like why we rationalize the denominator. Like I think it is perfectly okay to leave it as 1 over square root of 2. It's the correct answer, but this is the preferred answer. Does that make sense, guys? Okay, so I come back over here, and I know that both of those legs are square root of 2 over 2, so I'm going to write square root of 2 over 2, square root of 2 over 2. And then zoom out and look at that beauty that you guys just created. Wasn't that cool? All right, so here we go. Go to the next page, and it's going to say intentionally left blank. As a matter of fact, leave it blank for now. Go to the last page. We're going to come back to that third page, don't worry. And look at that. We have a blank unit circle for our entertainment. Isn't that cool? Let's start filling it in with what we know. So what do you want to do first? The degrees? 0, 30, 45, 60, 90. And then just continue the pattern, guys. 120, 135, 150, 180, 210, 225, 240, 270, 300, 315, 330, and then finally 360. If you did everything correct, you should end up with a full revolution 360. What should we do next? The coordinates? The radians? All right, let's do the coordinates. We know that the radius is 1. So this is a 1, 0. Let's do the easy ones first. 0, 1. Go to 180 degrees. So that's going to be what? Negative 1, 0. Go to 270. That's going to be 0, negative 1. Okay. Now here we go. Fill in quadrant 1. Square root of 3 over 2. 1/2. That's what we got, right? Square root of 2 over 2. Square root of 2 over 2. 1/2. Square root of 3 over 2. So fill in those, and then we'll talk. All right. Everything is symmetric, guys. It's a circle. Everything's symmetric. I have a y-axis, I have an x-axis. In quadrant 2, the x's are negative and the y's are positive. So at 120 degrees, look, don't circle this, just listen. This coordinate right here is symmetric to this coordinate that I'm circling right here. Do you guys see that? So all you're going to do is transfer the magnitude, make sure that the x value is negative. Negative 1/2, positive square root of 3 over 2. Do the same with the other coordinates, guys. Negative square root of 2 over 2, square root of 2 over 2. Negative square root of 3 over 2, positive 1/2. Yay or nay? In quadrant 3, it's the same, but in quadrant 3, both the x and y are negative. So, Chav, what's symmetric to what? It doesn't matter. You can fold the x-axis. This one right here, don't write this down. Just listen real quick on this. Those 2 points are symmetric. Do you guys see that? Transfer the magnitudes, make them both negative in quadrant 3. So transfer the magnitudes, make them both negative. Negative square root of 3 over 2, negative half. Negative square root of 2 over 2, negative square root of 2 over 2. Negative half, negative square root of 3 over 2. Do you see what we did, guys? Okay. In quadrant 4, again, take a quick pause. If you're about to fill in quadrant 4, this coordinate right here is symmetric to this one. See? Transfer the magnitudes. In quadrant 4, what's negative? The y. So make the y's negative. Keep the x's positive. 1/2 negative square root of 3 over 2 square root of 2 over 2. Hold on, I'll put a little square root of 2 over 2, negative square root of 2 over 2, and then square root of 3 over 2, and then the negative half. So you should have something that looks like this now. How do we feel? All right, here we go. 0 radians. Let's see, which ones are the easy ones? The 180. At 180, it's pi. If I do 1 revolution, it is, and at 90 degrees, that is pi over, those should be the easy ones. Oh, wait, the 271. 1.5 pi, or 3 pi over 2. All right. What did we say 30 degrees was? Do you remember? Go to the previous page. We said it was pi over, so put that one for 30 degrees. And then we said 45 degrees was what? Pi over 4. And then we said 60 degrees was pi over 3. All right, I'm going to show you a hack. So you know what? Put your pencils down. Here's the hack. Ready? This distance here, you just told me was pi over 6. Yes or no? Well, this distance here is also pi over 6. Yes or no? Well, you're pi over 6 away from having a whole pi. That's pi right there. So take a guess. What do you think it is at 150 degrees in radians if you're only pi over 6 from a whole pi? There you go. Look, you just did it. 5 pi over 6. You're not a robot. Let's do it. Let's do it again. Don't worry. Don't worry. Just focus real quick. I'll give you time. Let's do it again at 135 degrees. So this distance here that I'm putting right there, that's pi over 4. So then that means this is pi over 4. I'm pi over 4 away from a whole pi. What do you think it is at 135? 3 pi over 4. See? So one more. What do you think it is at 120? 2 pi over 3. Now you can go ahead and fill it in. If you don't like that, relax. You can just multiply all of them by pi over 180. It's no big deal. Ask questions, guys. Ask questions because I can't read mine. No, it makes sense all the time, forever. That's what's beautiful about math. Look at this. Look, check this out. It also works on every quadrant. Quadrant 3 as well. Look, this gap right here, that's also pi over 6. That gap is pi over 6. So if I go pi plus 1/6 of pi, what do you think it's going to be? Yeah, I heard someone say it. 7 pi over 6. You're damn right. Oh, can I say that word? Yeah, I think I can. You're correct. Did I say a bad word? Okay. YouTube, I'm sorry if you heard me say a controversial word. I promise it was all in love and heist. Okay. Because, we're going fast here. You know what? I'm going to make sure to edit that out because it was weird. 247. All right. All right. Cool? What's the next one? Yeah, you do. 5 pi over 4. What's the next one? 4 pi over 3. Look at that. Beasts. Beasts. Ask. Go ahead.
So pi plus 5 to 5 plus
How did I get the 5 pi over 4? How did I get which one? Got it. I got you, miss. This gap right here in green, that's pi over 4. I'm pi over 4 more than a whole pi. So it's like doing this. A whole pi plus pi over 4. I can just get a common denominator. 4 over 4. OMG, look. 5 pi over 4. Ask. Oh, I got that first from way back here when I was telling you guys to find these. Did I put it down? No, I didn't. I did it like this. I go 30 degrees times pi over 180, and then 3 goes into 18 6 times, so pi over 6. You can multiply everything by pi over 180. And if you don't like what I'm doing right now. You know what I mean? You do the same. That's for 30. You do the same thing for 49. You do the same thing for 60. Yeah, you can do the same thing for 150 degrees. You know, like look, 150 times pi over 180, and notice that 3 goes into 15 5 times, so 5 pi over 3 goes into 18. What did I just say? I already forgot what I was doing. Oh, yeah, 5 pi over 6. What am I talking about? There it is. Wait, look, check it out. Here's with the calculator. You see how it's pi over 180? So I can just go 150. I'm not going to put the pi in there because it's going to give me a decimal. So I'm just going to go times 1 over 180. Times 1 over 180. And then I'm going to push enter, math, fraction, enter. 5, 6, put the pi on the top. You know what I mean? Okay. All right. Check it out, guys. Hopefully you guys are having good conversations. Look at this gap here. That gap is pi over 6. I'm pi over 6 away from a whole 2 pi's. From a whole 2 pi. Is that a whole? From 2 pi. I'm pi over 6 away from 2 pi's. So this at 330 has to be 11 pi over 6. Yay or nay? Yes. What about at 315? 7 pi over 4. What about at 300? 5 pi over 3. A long time ago, I had a football player, and I did exactly what I did with you guys, and he was like, and I'm not following along at all. So because he was a football player, like, you know, he knows about like the plays. You got to be at this point at this time. I knew that he was very meticulous about, you know, like plays. Like you got to be at this spot at this time, blah, blah, blah. So all I did was just one little hack. I go, look at it as a pattern. Don't even worry about like what is what. Just like in football, like blah, blah, blah. Okay, I know you guys don't know what I'm talking about. Here's what I'm trying to say. All I told him is, this is a circle. Everything is symmetric. Know the first quadrant. So if you know the first quadrant, you know everything. So this you can't do anything about the first quadrant. You gotta know. Core not. Look at the symmetry. The denominator. That's a 3. That's a 3. That's a 4. That's a 4. Look down here. That's a 4. Look over here. That's a 4. Like you see how the 4 is in, like the denominator stays the same. In quadrant 2, look at the numerator. In quadrant 2, the number is 1 less. Pi over 3, quadrant 2. 2 pi over 3. In quadrant 3, the numerator is 1 more than the denominator. 7 pi over 6. 5 pi over 4. In quadrant 4, double the denominator, subtract 1. Double the 6 is 12, subtract 1 is 11. But you gotta know the first quadrant. From the first quadrant, everything else is symmetric, and then just know the game. Quadrant 2, 1 less. Quadrant 3, 1 more. Quadrant 4, double, subtract 1. Does that make sense? And after that, that kid got hundreds and all I did in circles. Because, you know, that's what he needed. Now, I don't want you to memorize. I want you to really know it. But do you see why? Cool or not cool? Okay. Here's the last. Look at all this beautiful math you guys just did, guys. Here's the last thing we're going to do. And then after this, we'll call it a day and you can do your delta. on the intentionally left blank page, go to that. And let's exaggerate quadrant 1. I'm going to draw one random angle, or triangle, I guess. This is my theta. This is coordinate x comma y. This is my radius. My radius is 1. And I'm going to write, for now, SOHCAHTOA. You don't need to write SOHCAHTOA anymore if you already know what is what. But if until we're beasts, we're gonna continue writing SOHCAHTOA to help us out. It's just an acronym. So what this acronym tells me, it tells me that sine of some angle is opposite over hypotenuse. So here's my angle, opposite. Well, let's write these letters here. This distance here is an x distance, and this distance here is a y distance for that xy. Do you guys agree? All right. So sine is y over 1, which is just y. Yay or nay? Okay, and then cosine, I'll slow down. Cosine is adjacent over hypotenuse. Adjacent happens to be x. Hypotenuse happens to be 1. So because anything divided by 1 is itself, I can just say that cosine is just your x. Does that make sense? Okay, so on the side, I'm going to write cosine theta is simply x, and then sine theta is simply y. This is true as long as the radius is 1. And I'm going to put that in a nice little rectangle. All right, Chav, so why is this important? Okay, let's look at, why is this important? Because if I tell you this, cosine, let's see if you guys can get it in the first try. Cosine 60 degrees. What do you think this is? You have a unit circle that has 60 degrees on it, right? Go to the 60 degrees. What is the x coordinate? So this is probably a half, no? I don't know. Let's see. Let's using context clues. Here's a calculator. It's in radian mode. Let me change it to degree mode. Let's see if we're fake or if we're real. Cosine. Let's see if we're posers. I push 60 and I better get half. OMG, look at that. We're not posers. Oh yeah. Don't worry about that. Don't worry, guys. We're almost done. Here you go, guys. If I write cosine of pi over 3, let me write the pi over 3 better because I don't like using it. Pi over 3 like that. Pi over 3 is the same thing as 60 degrees. It's just a different way to measure rotation. So if I change my calculator to radian mode, so here I am going to radian, and I'm going to go cosine of pi over 3. Am I going to get the same answer? Yes, I better, or else I'm a poser, and I'm not a poser, guys. I'm math life AF. Okay. Cool or not cool? Yeah, so guys, so now let's just do one more because let's not let cosine have all the fun. Let's do sine a little bit as well. So if I write sine of 60 degrees, you're going to tell me square root of 3 over 2. If I write sine of pi over 3, you're going to tell me square root of 3 over 2. How do we feel? All right, so today was an introduction to unit circles, so now we just got to get used to it. If you log into Delta, you're going to be having some of these questions like that, and you're going to be doing 2 questions real quick of recap of the Pythagorean theorem, x squared plus y squared equals z squared. And then you'll be doing some of this stuff, converting degrees to radians, radians to degrees. So easy, not that bad. Do we feel good, guys? All right, take care of business, and we're done, guys. Good job.